So great. So today we have Lev Rozansky from UNC. The title is on his first slide, link homology from a step of D to branes, probably with a B twist. Okay, Lev, please.
Thank you. So maybe the title is a little bit misleading. So I will try to make this talk more mathematical. But I also want to mention the superstring origin of or interpretation of this construction. So let me begin with so-called Homology PT polynomial. It's a part of three-dimensional topology. So to a framed oriented link in a three sphere, it assigns a polynomial in two variables, which may also be inverted, q to the plus minus 1, a to the plus minus 1. And in fact, it's not quite a polynomial. It may have a controllable denominator of the form q minus q inverse to the number of link components, but it's just minor nuisance. So a big theorem that was proved by all these 8 people, maybe 35 years ago, is that there exists a unique non-trivial link invariant, this polynomial, which has the following properties. It's multiplicative. So if you have two links which are totally disjoint, the polynomial will be the product of their individual polynomials. It satisfies a very strange relation that if you compare 3 links which differ locally at a crossing, one has positive crossing, the other has negative crossing, and the third one has identity there, just strands going parallel, then these 3 polynomials will be related in this way. One minus the other will be q minus q inverse times the third. And there is a framing condition. So framed means that the link components are not exactly thin lines, they're very thin strips. So when you have a kink like this, then the strip has a 360 twist. And removing this twist creates a factor of A or A inverse, depending on which way you twist it. So as an example, one can derive immediately the value of the polynomial of the unknot, of a single unknot. For that, you close the skein relation by 2 arcs. So you get 8 figure minus 8 figure equals q minus q inverse times double unknot. And then applying skein relation and multiplicativity, you see the eight pictures are in fact unknots with a twist. So you have a relation on the polynomial of the unknot, and if you assume that it is non-zero, then it must be A minus A inverse over Q minus Q inverse. So this was a very puzzling, I think, story in low-dimensional topology back then, because this polynomial did not have a simple or any, in fact, explanation in terms of classical topology. For example, you couldn't express it in terms of the fundamental group of the link complement. So link homology is categorification of this construction, meaning that now to a link we want to assign a vector space with 3 gradings, I, j, k, which is called graded link homology, so that the polynomial itself is the graded Euler characteristic. So the first index just gives you the sum, it's the homological index, and the other 2 are reflected by powers of variables q and a, and the result should be the link homology. And it's a bit more complicated. One has to show that to a link cobordism between 2 links, you associate a linear transformation between these 2 vector spaces. So this link homology was constructed by a sequence of papers. In fact, first there were papers by Zergel, who introduced so-called Zergel bimodules. Oh, by the way, I should have mentioned that the skein relation also appears in algebra as so-called Hecke algebra relation. Hecke algebra is something you construct out of symmetric group, in fact, by imposing, or sorry, out of the braid group, in fact, by imposing this relation. So you may say that it is a deformation of the group algebra of the symmetric group. So Zergel was working on the categorification of Hecke algebra by Zergel bimodules. Then there were the work of Raphael Rouquier, who created Rouquier complexes to categorify skein relations. And then we had papers with Misha Kovanov. The best presentation of the categorification was applying Hochschild homology to Rouquier complexes. So I will skip the story. It uses just commutative algebra to create link homology somehow. So what do we do with Alexei Oblomkov? This is our joint work. So we use a certain feature of what one might call symplectic algebraic geometry. So it's algebraic geometry of symplectic varieties. So physics suggests that to a symplectic variety, one can associate a two category whose definition or definition of morphisms between objects there uses the notion of matrix factorizations, which is unfortunate because matrix factorizations are not very popular in algebraic geometry, although some people use them. In this two category is not very popular either, although I think it is as important for symplectic varieties as the category of coherent sheaves is important for ordinary varieties. So it came from our work with Anton Kapustin and Natalia Saulina. We consider a family of quiver varieties, rather simple ones, which correspond to this quiver. So when R, the dimension of the box, is 0, the corresponding variety is the so-called commuting variety. Its points are pairs of square matrices which commute with each other, and then you take quotient by conjugation by GLM. It's a singular variety, but it's a useful one. Then when R is equal to 1, by a certain miracle, you get Hilbert scheme of n points on C2. This is
Lev, excuse me. Will you work with varieties or with stacks? How important?
I will. So I will work with all of them. I will present them as quotients of stable parts of cotangent bundles.
Okay, so you need some stability.
Yes, stability will be there. In the first case, there, as far as by the way, my knowledge of algebraic geometry is very, very thin. So if I say something wrong, please correct me, and I will appreciate because it will help me. So in case of R equal to 0, there is no stability. In case of R equal to 1 or higher R, there is a stability condition which turns these into smooth varieties. For example, Hilbert scheme of points. And generally, it's a resolved moduli space of instantons on C2. So this is what we use. In each of these two categories, we select a special object, which I call FL, because it is related to the cotangent bundle to flag variety. And we consider the category of its endomorphisms. Since the whole thing is two category, endomorphisms form a category, and since you can compose them, it's a monoidal two category. The monoidal structure is composition of endomorphisms. So it's one level above the usual categories, say, of coherent sheaves, where endomorphisms would form an algebra. So in particular, the endomorphisms in case of R equal to 0 commuting variety will be equivalent to the category of GLN equivariant sheaves over so-called derived Steinberg variety. And then we take the affine braid group. It's the usual braid group, except that you use annulus instead of a disk. So the points which travel along the strands of the braid live on an annulus here. And the whole of the annulus is denoted by this red line. If you take the quotient of the group algebra of affine braid group by the Kane relation, you get the affine Hicke algebra by definition. And second remark is that there is a homomorphism from affine braids to ordinary braids where you just plug the hole. So then annulus turns into a disk and your affine braid becomes an ordinary braid. Our main results with Alexei is that we construct a homomorphism from affine braids into this monoidal category of endomorphisms. Braid becomes a braid with a hat. In case when R is equal to 0, the commuting variety story, it matches the Bezrukavnikov-Risch construction where they represented a affine group by action on equivariant coherent sheaves over derived Steinberg variety. When R is equal to 1 and the symplectic variety is the Hilbert scheme, we show that this homomorphism factors through ordinary braids.
Will everything be derived?
Yes, you can say yes, so you can safely add the word derived, although it's not always necessary. So this way we get a homomorphism from ordinary braids into a new category of endomorphisms of FLN1. It's similar to Steinberg variety somehow, but it's different. And we define it as a category of matrix factorizations. That's what I'll explain. And finally, we show that if we take a home between from the image of the identity braid to the image of a braid, and we do here something, I'll explain it a little bit later, what we get is the homology of the link, the one that was previously constructed through Zergel bimodules. There is a notion of tensor multiplying by exterior powers of defining representation of GLN. And if you do this, then the degree of the exterior power will match the A degree in the link homology. So the A degree comes from these exterior powers. And if you equip this sum of exterior powers with a certain differential, you create a Kazoo complex out of it, then you will get categorification of Reshetikhin derived polynomial, in fact, for supergroups. So GLN in particular as GLN0, but also for other supergroups. And if you consider higher framing dimensions, if you go to instantons, then the homomorphism into the category of endomorphisms categorifies the cyclotomic Hecke algebra.
So what is Q?
Sorry?
What is parameter Q?
The
categorifies its cyclotomic Hecke. There is a Q there, yeah.
Yes, so it's the same Q that appears everywhere. There are parameters. There are, if I remember correctly, so in cyclotomic algebra you have other parameters which become line bundles over just a moment. We'll have certain CPN, and the line bundle there will be the cyclotomic parameter. So let me comment on that later. I'm a little bit rusty with the cyclotomic part, but it appears, say for the case of n equal to 1, your quiver variety, the moduli space of instantons, will be simply projective space. So the line bundles over that projective space will categorify the parameters, the cyclotomic parameters. Let me quickly go over the M-theory interpretation of what goes on, and I'll come back to it later. So the link homology appears as the space of states of BPS particles in a special 5-dimensional supersymmetric quantum field theory. So that's slogan number 1. This was suggested by Gukov, Schwartz, and Waffa at the time when we were categorifying for Zergel bimodules. So the space of, another general fact is that this space is determined by categorified curve counting in a special 3-dimensional Calabi-Yau, which is O minus local P1. In the presence of special Lagrangian submanifolds in this CY3, which remember the link in S3.
So I'm a bit outdated. Are you talking about counting of curves open BPS states, like curves of
Yes.
general with boundary on the Lagrangian?
Yes, exactly. So those curves will have holes, and the boundaries of those holes have to sit on those Lagrangian submanifolds.
Is it mathematically kind of justified? The state of art now.
There were
was a
papers.
problem.
So I refer to papers by Gopakumar Waffa, Guri Waffa, Labastida Mourinho Waffa, where this concept was discussed and certain methods were suggested.
I don't see a mathematician among this gentlemen.
Okay, so it's again, consider this as suggestion.
Okay, all right.
So I listed the theorems that we proved with Alexei. These are rigorous statements, but the motivation comes from the suggestion that it comes from curve counting.
And you will explain how to categorify this naive count of curves with a boundary on a non-compact Lagrangian, yeah?
Yes. So our way of I'm sorry, just a moment. My computer is a little bit. Just a moment. Sorry. Technical difficulty. My OneNote somehow. Okay. Let me go back. It doesn't like large files. Sorry. So our way of curve counting from the string perspective is to put Lagrangian submanifolds into a special position so that the curve folds into a stack of disks. An example would be a singular curve that you're familiar with, y to the m equals x to the n, which corresponds to a torus knot. In fact, this is inspired by the paper of Diaconescu, Shende, Waffa, in which they were explaining previous work of Oblomkov, Shende, relating homology of torus knot to certain constructions over singular curves. So suppose that here we insert a small parameter epsilon, which is very small. Then the singular curve becomes, it folds into disks with some special points, but in physics, this doesn't matter. So the picture for 2,3 torus knot would look like something like this. If you look from above, there will be two overlapping disks. One, in fact, it's the same. It's it's a singular disk because they are part of the same curve. But again, if you flatten, what you see is multiplicities. And one disk goes out of the other, they exchange. Now, the whole thing happens in C2. Again, I'll come back to it later. So if you take a slice through this dashed purple line and add 2 more dimensions, which are not seen in the first picture, then this is what you see. The green rays are slices of these 2 disks, which
the C square, should it be thought as a fiber in this O
yes,
minus?
it's a fiber over the north pole of P1.
Okay.
Everything flattens, and the disks are rays in this picture. They project onto the purple line, which is the dashed line in the first picture. So you see multiplicities 1 and 2, but they also project on this extra C, which you do not see in the first picture. And on the extra C, they represent the points of the braid. So as the purple line would rotate in the first picture, in the second picture, the green points will move on the vertical purple plane.
Somehow I missed this purple explanation. So from the point of view of the resolved conifold, this purple direction is what?
There are 2 C's which form the fiber of O-1 plus O-1 over the north pole of P1.
You break the symmetry of them somehow arbitrarily?
Yes, I break the symmetry between them. So it's broken by the positioning of Lagrangian submanifolds. So the disks, the folded curve, will lie. It's the same as inserting this epsilon, which makes y small, whereas x is not small. X and y are coordinates in these 2 fibers.
Mm-hmm.
So the curve flattens into a disk which lies in one C, and the braid happens in the other C. I will come back to this picture if I have extra time. So it's just the motivation for math that will emerge. So the vibration of the stack of these green disks is governed by a 3D B model. It's a QFT whose target space is Hilbert's scheme of points on C2. This C2 exists elsewhere. It's not part of these pictures. I will explain it later. And the object that we're talking about is one of possible boundary conditions for these disks. So the boundary is compressed, so you see single disk. You do not see this 1 to 2. You do not see individual lines. You just compress them. And this creates the object FLN1. So a similar approach can be used for the case of T star S3, and it will lead to Rina Anno's construction of Kavanagh homology and its annular generalizations, but it's a separate story. So again, the idea is if you want one way to count curves, which are related to Lagrangians, is to put Lagrangians in such a position that curves almost coincide. And then you can apply the method of 3D B model to do the counting.
Yeah, but I'm confused. Do you have a freedom to put your Lagrangian in the position which you like?
It's an interesting question. So here we will need a physicist to comment more firmly on this. As far as I understand, small movements of these Lagrangian submanifolds generally do not change the spectrum of BPS particles. So therefore, for example, this is what Diaconescu Shendewafa used to explain getting torus knot homology out of singular curves. They were moving the Lagrangian submanifolds.
No, since you used somehow, I don't know. Are you talking only about torus knots, or it's more general?
So the point of our work is that you can apply this to a general braid, to a closure of a general braid. So you have to present your link as a closure of a thin braid inside S3, and then you can, again, I'd rather talk about it at the end when, if I may, after I cover the math side. But the idea is that this works in general for any link presented as a closure of a braid.
Okay.
And this is, and the physics is different from Diaconescu-Shendewafa. I will also comment on that. They're working on the mirror side. I will explain what I mean later. So let me go back to math and explain the two categories that you associate to a symplectic variety, or at least in a particular case. So naive geometric idea of these two categories is that the objects would be Lagrangian subvarieties of the symplectic variety, and the objects will be fibrations over these subvarieties whose fibers live elsewhere. So fibers exist separately from X, SM. This is a picture. And the naive idea of the category of morphisms would be intersect Lagrangian subvarieties, take their intersection, and take the product of fibers over that intersection and consider coherent sheaves over it.
Probably in the derived sense, yeah, because they can be tangent.
Yes, in an unusual. So yes, as you will see, the rigorous definition will do something somewhat unusual to this. Yes, this require, and it's not a naive derivation. It's not how you would intersect sheaves. It's something else. So as you mentioned, these first of all, these Lagrangian subvarieties may be singular, and their intersection may be bad. This is the first consideration which inspired us to look for a better defined answer. For example, if your symplectic variety is cotangent bundle to C, a good intersection would be just two lines intersecting at the origin. That's where intersection looks locally as intersection of their tangent spaces. And the bad intersection would be, for example, a parabola intersecting a line where they touch. And since this is algebraic geometry, you cannot simply deform a parabola to a generic position where intersection will split into individual transverse points. You have to do something else. So the answer is you have to present the Lagrangian subvarieties, for example, p equals 3x squared, in terms of generating functions or actions as a graph of derivative or differential of a function. 3x squared is the derivative of x cubed. And then the category of intersection will be the category of matrix factorizations of this x cubed, which one way to define this category is, and it is a more conceptual way, in fact, is to take derived category of modules of C of x mod x cubed. Note that it is x cubed, not x squared here. And declare all the finite complexes to be zero objects. So you should look at infinite complexes there, which happen to be periodic. So here is a rigorous approach to the definition of the two categories. So first of all, we need a quick review of matrix factorizations as a homology category. So let X be affine, and in fact, to make it simple, I will even assume that this is Cn. W is a polynomial over X. And the category of matrix factorizations is deformation of derived category of modules described by this W. W is an element of Hochschild cohomology of degree 0. So you use it to deform the category. So the derived category of modules can be folded a little bit if you reduce Z grading to Z mod 2 grading. So let's ignore the Z and just follow even odd. Then a complex of modules can be presented as two modules, the sum of even ones and the sum of odd ones. The differentials will shoot both ways between them. And the square of differentials will be equal to 0. That's the usual story in which you ignore the full Z grading. In matrix factorizations, your object is very similar. It's a complex of two free modules. So we instead of working with derived, we work with homotopy category of free modules. So you have two free modules of equal rank, in fact, related by differential, whose square is equal to W. So for example, if your variety is C with coordinate x small and your W is x cubed, then an object in the category would be this, C of x into C of x, one way by x, the other way by x squared. So this is a simple example of matrix factorization. The rest of the story is the same. So although the differential here doesn't square to 0, nevertheless, if you consider home between two matrix factorizations, consider home between the modules M1 plus M0 just as modules over the algebra C of x, and it will have a genuine differential defined as usual as a commutator with inner differential of complexes. So the funny fact is that this differential, the commutator, squares to 0. This is a consequence of Jacobi identity and of the fact that W commutes with everybody. So then you define home between two matrix factorizations as the homology of this differential, acting in all the homes between the modules. Does this make sense?
Yeah, it does. But you don't have Z grading, so it's not really.
So we have only Z mod 2 grading. So the key thing is that the usual definition of what is morphism between two chain complexes is you take home, which commutes with the differential, up to homotopy. This is the same as saying that you take all the homes between chain modules, which, and there you have a differential, which is a commutator with the differential in the complexes. So being closed is equivalent to commuting with the differential of complexes, and modulo exact is up to homotopy. So here you can repeat it verbatim.
So the HD is also a super space, right?
Yes, everything here is Z2 graded.
Z2 graded. Yeah, thank you.
So essential properties of this category of matrix factorizations is that, first of all, it resides in an infinitesimal, in a formal vicinity of critical locus of W. The partial derivatives of W are exact. Their commutator is of partial derivatives of D with D. By the way, you can think of this D capital as a square matrix whose entries are polynomials because it relates to free modules of equal rank. So partial derivatives of W are homotopically trivial. So you can say that the category of matrix factorizations is properly derived coherent sheaves sitting on the critical locus of W. If critical locus is good, which means it's smooth, and the matrix, the Hessian of W is non-degenerate in transverse directions, then I'm cheating a little bit. The category will be the same as category of coherent sheaves over the critical locus. The second feature is so-called Kazoo duality. You can trade even variables for odd variables. So if you consider matrix factorization whose W is linear in variables A. So I can have here several, I give them different names to distinguish their roles. Each variable A multiplies polynomial of x's. Underlying means there are several. Then this would be equivalent to modules to something more familiar. Just a moment. You have modules over x's and thetas, odd variables, and your W turns into differential, which kills the polynomials P. So if polynomials form regular sequence, then this is the same as modules over C of x modulo the ideal generated by these polynomials. So if you see linear W, you can simply turn it into coherent sheaves over the quotient by these factors. In particular, there is so-called Knorr periodicity, which says that if you have two variables x, y, and some other variable z, and your W is xy times polynomial of z, then this is equivalent. You can simply drop both x and y from the picture. And finally, you can tensor multiply matrix factorizations over the same variety. And the result will be matrix factorization of the sum of W's. So this is an important fact, because the square of the sum is equal to the sum of squares if the terms anti-commute, as they do, because these are differentials in two different complexes. So the anti-commute in the tensor product, and this drops off. So when you tensor multiply matrix factorizations, there are W's in. So now we can go back to symplectic geometry and define the two categories of the cotangent bundle. So the simple part, let's compare algebra and geometry. We assume that x is just Cn with coordinates x. An object in the two category is a polynomial. On the geometry side, we take the graph of its differential, which is a Lagrangian subvariety in T star x. The category of morphisms on the algebra side is matrix factorizations of the difference of W. So W is an object. Morphism between two polynomials is category of matrix factorizations of their difference. And on the symplectic side, on the geometry side, what you see is that the intersection of Lagrangian subvarieties in the tangent space projects down to the base. Just a moment, something moved here, I'm afraid. Yeah, I'm sorry, the frame moved up. I don't know why it moved. So I'll not try to, the x-axis was supposed to go here. Let me draw it. Sorry. I'll draw it as a dashed line to distinguish it from the wrong one. Just a minute. Sorry. Technical difficulty here. So the x-axis was supposed to go this way. So the intersection of Lagrangian subvarieties projects to the base bijectively onto the critical locus of the difference between W2 and W1. So if you assume that the category of matrix factorizations is coherent sheaves over the critical locus, then it matches exactly the naive expectation that one should take coherent sheaves over the intersection of Lagrangian subvarieties. But if the W2 minus the critical locus is not good, then you get something different, so you should take matrix factorizations. So the presentation of Lagrangian subvarieties in terms of W's actions seems to be critical for proper definition of those two categories.
Do you need some transversality, some genericity of the pairs, for example, W1, W2, or it will disappear when you use an appropriate language like derived intersection? For example, if W1 equal to W2 for people here working in C infinity settings, that's a problem when to define morphism between in Fukaya category between two non-transversal. Okay, here it's the holomorphic story, and so what?
So here there is no problem. That's the good part of it. We don't care whether intersection is good or bad in the cotangent bundle, because the proper category of morphisms is matrix factorizations of the difference of W. So if both W are equal to each other, then we simply get matrix factorizations. W then is 0, so differential squares to 0, and you're back to ordinary matrix, to ordinary coherent sheaves. So there is no difficulty. So the derived version of the intersection of Lagrangian subvarieties is the category of matrix factorizations. So that's how you derive it. You take matrix factorization of the difference of generating functions or actions. In physics, W's are called superpotentials. So let me call them superpotentials. The composition of morphisms, again, is simple. So if you have morphism M12 matrix factorization from W1 to W2 and M23 from W2 to W3, you simply tensor multiply them. The superpotentials add, so W2 cancels when you add these two differences, and you get the W3 minus W1, the matrix factorization of W3 minus W1 as you wanted.
Excuse me, Lev, just clarification. Do you take derived categories, so homology categories of matrix factorizations? So, or do you take the DG categories for morphisms?
I'm not an expert there. I think DG is better because you can form cones and so on.
Okay. Yeah, just that it's then it's equivalent to the derived category of coherent sheaves in the sense that it's homology categories equivalent.
So whatever you would do with coherent sheaves, just do it with matrix factorizations. Again, the matrix factorizations is a deformation of coherent sheaves in the precise sense, because you consider W as an element of Hochschild cohomology. Usually people take the elements of degree 2 because they want to preserve the homological grading. But if you sacrifice homological grading, then you can take any element, any even element in Hochschild cohomology and use it to deform. So here you just take W.
Thank you.
So we need more general objects. For example, if you want to describe a vertical line, a fiber in T star C, you cannot describe it by W, so you introduce auxiliary variables. And the superpotential will be A times X, and the formulas applied to describe the Lagrangian subvariety is momentum is again derivative with respect to x, and you set the derivative with respect to a to be equal to 0. So you get x equals to 0 and p equals to an arbitrary variable, to free variable a, and that will give you a vertical line. So generally, an object of this two category is a pair of auxiliary variety z and w, which is a polynomial over x times z. And the category of morphisms is matrix factorizations over x times two auxiliary varieties of the difference of superpotentials as usual. And if you want to compose, there is the usual story about pullbacks and push forwards applied to z's, whereas x remains the same. So this is a marriage between classical mechanics. I think people who graduated from Russian universities were subjected to it. Just there was no choice. And they're more familiar with these W's appearing there in the, what was the name, Hamilton-Jacobi equation. That's where they appear in classical mechanics, sometimes called analytic mechanics. So here you combine that story with algebraic geometry. There is an equivariant version of this. When a group acts on X, it will act naturally on cotangent bundle. And so you can define an equivariant version of this two category. An object would be.
Yeah. No, I mean, what is equivariant Lagrangian? Ah, you consider only graphs of differentials.
Yes. So, yeah. So W will be an invariant function of both Z and X. And the category of morphisms will be equivariant matrix factorizations of the difference. Here is a remark. Presumably, thus defined, this two category of the cotangent bundle is the same as the two category of representations of the category of coherent sheaves taken with monoidal monoidal structure given by tensor product. So take a variety X, take coherent sheaves. You can tensor multiply them. This gives you monoidal structure. Now you can ask a question, what's the two category of representations, whatever this means. So I could go a little bit into this story with some examples, but let me just skip over. How does it appear if you take zero section of T star X? That's a Lagrangian submanifold defined by W equal to 0. So its endomorphisms will be exactly coherent sheaves over X. Then any other object becomes a module over the endomorphisms. And presumably this will give you an equivalence. Given this, why do we use, of course, it's nice to know that this two category of representations is related to symplectic geometry, which is just funny in its own right. But our approach gives a certain advantage. Namely, we can remove a certain part from T star X and still define a two category. Suppose there will be stability, there is some stability condition, which requires us to take an open subvariety of T star X. Then we can still formulate the two category by using the following. X times Z maps into T star X in a very natural way by W. And we just take, so first of all, dW sends it into T star X cross T star Z as a graph, and then you project, forget about T star Z. So you take preimage of the open subspace, subvariety, T star X stub, and use it in defining matrix factorizations. So your matrix factorizations will not be over X times Z1 times Z2, but rather over a certain subvariety of it, specified by the stability condition. So that's why we can define two categories associated to quiver varieties together with the stability condition. Okay, so now we go directly to quiver varieties. We begin with the commuting variety, which is simply Hamiltonian reduction of T star of GLN with respect to a joint action. So its two category will define as GLN equivariant to category of cotangent bundle to Lie algebra GLN. Let me remind you that a Springer resolution is mapped from T star of the flag variety to GLN. I identify GLN with its dual. Let me ignore the distinction. So our object that we use is T star B used as auxiliary variety, and W is the trace of product of moment map and coordinate on GLN, the matrix of GLN. So that's what it is. Now, you may ask, why is auxiliary variety itself symplectic? And this is an interesting story, which this requires a separate explanation, why this one turns out to be symplectic. It's because this story is a part of a certain four category related to Kapustin, Gayot, Witten. So the full story would be a story about four categories. So there are some miracles which happen. Okay.
I missed somehow. What is the problem about what symplectic?
It's not a problem. It's a little bit strange. The auxiliary. So this T star B.
Yes, which is symplectic because it T star B.
Yes, but it is an auxiliary variety, so it didn't have to be symplectic. And in fact, there will be more examples where this one is not symplectic. So you may wonder, why should this particular one happen to be symplectic in its own right? Mm-hmm. And the symplecticity of T star B has nothing to do with the story. It just exists by its own. So there is a question why.
So for other ranks, it will not be symplectic, like R equal 2?
It's not related to R. It's always symplectic.
Right.
Yes. So this particular one is always symplectic, and it's special, and there is a special reason why. This happens as a certain intersection of two quivers. You see, this is a quiver variety. So in the story combines two quivers, an affine quiver, which gives you symplectic variety, and the linear quiver, which gives you the object. And so I could, if this is a separate subject, how they intersect and combine into a single story. Maybe I'll say a little bit after I finish the rigorous part. So symplectic geometry of this object is, well, it's known inside the commuting variety, which is pair of commuting matrices. You take a subvariety where matrix Y is nilpotent, and on top, that's the Lagrangian subvariety of this object. And on top of it, you have fibers, which are flags preserved by both matrices X and Y. So in other words, the object is a flag commuting subvariety restricted to the piece where Y is nilpotent. And the endomorphisms of this object is matrix factorizations. Now you have, first of all, they're GLN equivariant. And you have to take two copies of cotangent bundles because you have two copies of the object. It's home from object to itself. So you have two copies of the auxiliary variety and the base GLN. And W is difference between moment maps times X. The critical locus of this is something awful. So it's double flag commuting variety restricted to Y being nilpotent. It's totally horrible. It's not even a full interest. It's not even a complete intersection, as far as I understand. So one should not try to work with coherent sheaves over this. Actually, we tried when this whole story started, and that's crazy. The right answer is matrix factorizations. This is a very nice category. Can be simplified. As you see, matrix X appears linearly in W. So you can do Kazoo duality, trade it for odd variables, which create a differential killing mu2 minus mu1. And you will end up with the derived Steinberg variety, because the condition mu2 equals mu1 is not a regular sequence. So for that reason, so it's mu1 and mu2 are nilpotent matrices which sit on top of flags in T star B. So mu2 equal mu1 says that the matrix is the same. So you have one nilpotent matrix and two flags. And this is Steinberg variety, except you have to derive it because it came through Kazoo duality from this superpotential. So Bezrukovnikov-Risch appear naturally within this story. And you don't have to guess that it must be derived. It just comes this way through Kazoo. So if you ask,
Lev, I'm a bit of a confused. The mu earlier that was in the Springer resolution, that's also the moment map. And basically that here mu1, mu2 are the images from the cotangent bundle to the of the flag
Yes.
variety. So those are nilpotent matrix.
Yes, so mu2 and mu1 are both nilpotent. And so you have one, so now you have one
bundles from both.
So you have now one nilpotent matrix and two flags which preserve it.
Okay.
That's the Steinberg variety, but
that's a Springer fiber of this nilpotent variety, nilpotent matrix. Okay.
So you have two Springer fibers, right? Two flags.
Yeah, from two different nilpotent matrices.
Yes.
mu1,
Yes.
mu2.
Yes, and the matrix is nilpotent, and this has, and there are some remnants of the odd variables, thetas, which came from matrix X. You cannot remove all thetas, so that's why the Steinberg variety should be derived for this construction to work. The second way to simplify, there is another way to simplify this category. You can, let me say it quickly, you put one flag into the standard position by using GLN equivariance. So now you're left with with Borel instead of GLN. You lost your first flag, it's fixed. So you only have its fiber, which is nilpotent, strictly upper triangular matrices. You have the second T star B and GLN, and that's your superpotential. And now you can get rid of this nilpotent matrix by using linearity, or Knorr, same thing. It combines with the lower triangular part of X. So Knorr removes the first nilpotent, strictly upper triangular, together with the lower triangular part of X. So now you're left with Borel subalgebra of GLN, the nilpotent matrix is hanging over the second flag, and the matrix which parameterizes the second flag. And there are two Borel groups. One is the remnant of GLN, and the other one is related to presenting the second flag as quotient of GLN by Borel. So that's the simplest version of matrix factorizations that we use. Borel, nilpotent, and the group with this very simple superpotential and double Borel equivariance. So I'll just give you one example. Jan, please stop me if I'm over time and.
No, I don't want to stop you. Actually, just go on.
So I recognize. So example how this works for n equal to 2. So X Borel is upper triangular, Y is strictly upper triangular, and the flag is parameterized by this matrix. I assume that its determinant is 1. So the superpotential factors into 3 simple factors, A21. This is what tells you that the flag is rotated from the standard position. Y12, the only component of the Y matrix, and this expression. Setting this expression to 0 tells you that the flag is somewhat inverted, that you permuted the eigenvalues of the matrix X. X respects the standard flag, it's upper triangular, but on the critical locus, it must also respect the second flag. So X conjugated by G should also be upper triangular. And this is given by this condition that Z is 0. So to the identity braid, you associate this matrix factorization where A is the algebra of all these variables. You should by A21, which tells you that the second flag must equal the first flag. And there is an auxiliary differential shooting back to make your W. And the crossings come from this matrix factorization. You should by Z, which tells you that the eigenvalues of X are permuted. This is the ideology of Bezrukovnik of Risch. And you have the other differential shooting back, A21 times Y12. By the way, here I should also quote Arkhipov and Kanstrup, who were also exploring this representation of fine braid groups into matrix factorizations. I'm sorry, I forgot to quote them here. By the way, in this 2-category story, there is the Legendre transform, which flips 2 GLN matrices, which flips cotangent and the base. So Legendre transform appears as a 2-functor on this 2-category. If you apply it to the object FLN0, then you will get, instead of the Springer resolution, you will get the Grothendieck Springer. So you'll have the flag variety with any matrix, on top of each flag, you will put all matrices which respect it, not just nilpotent ones. And the endomorphisms of this object will, again, through the same procedure that we used. I'm sorry, my OneNote started to rebel against me. With the same procedure that we used to get Steinberg, now we'll get Grothendieck Steinberg. And that's the second variety used by Bezrukovnik of Risch. So the equivalence between coherent sheaves over equivariant coherent sheaves over derived Steinberg and over Grothendieck Steinberg is a manifestation of Legendre transform acting on T star of GLN. So it has a 2-categorical explanation. If you use the language of representations of monoidal category of coherent sheaves, then Legendre is not as natural. But here it's very natural. Okay, what happens when you bring in framing? The answer is not much. Oh, sorry. I should have said MN1, the Hilbert scheme. I'm sorry. So bringing of framing doesn't change much. You repeat the same story verbatim, just pulling it back to framing and adding stability condition. Sorry, just a moment. So this is 1. So all you have to do is add cotangent bundle of Cn, which is framing, impose the stability condition, which says that matrices X and Y of T star GLN acting on V on the vector must generate the whole Cn, and do the Hamiltonian reduction with respect to GLN. The object is exactly the same. It doesn't use the vector. The W doesn't use the vector, the auxiliary is the same. Its endomorphisms is again the same, except that you have to include Cn as part of the base. Now you have X and V, and you have to impose the stability condition. And the stability condition becomes this. Instead of the matrix Y of the Hilbert scheme of the GLM, you use the moment maps of these T stars. So this is what I said before, that it's easy to impose the stability condition on the symplectic variety into the category of morphisms. That's what you have to do. In fact, you may drop one of these conditions, we'll still get an equivalent category. Now, the matrix X participates in the stability condition, so you cannot trade it for odd variable by Kazoo duality. So you cannot use the trick that led you from matrix factorizations to derived Steinberg in this case. But you can still do the second version of simplification. So you could simplify this down to, oh, sorry. Do you see when I move it up? Because I see only blank page.
Yeah, yes.
Here it remerged. It just takes time. So you can still do this simplification in the R equal to 1 version. You will cross multiply it by Cn and impose the stability condition that X and Y, we do not assume that they commute here, acting on V, generate the whole Cn. So this will be the category for R equal to 1. By the way, note that matrices X and Y appear in this simplified version in a very symmetric way, except that X is upper triangular and Y is strictly upper triangular. So this is the source of a certain symmetry of link homology. Here it comes very naturally. But again, it's a separate story. So again, the category that you use in case of R equal to 1 is the same simplified one, except you add Cn for the vector and this condition. And the rest is the same again. So there is an obvious functor from endomorphisms in case of R equal to 0 to endomorphisms in case of R equal to 1. You simply pull back to this extra Cn and then restrict to the stability condition. So this F1 is very easy. So
is it kind of a bit confused because you have the potential.
It doesn't contain V.
Is an open part. Okay, yeah, maybe.
V does not participate in it.
Mm-hmm.
So it's just a pullback. And our theorem is that if you send ordinary braid, so if the ordinary braids in here, sorry, the theorem is that going around the hole becomes trivial. The reason is that the stability condition punctures the P1, whose line bundle gives the affine element of the braid. So the affine braid, which takes the innermost strand and takes it around the hole, is represented by tensoring with a certain line bundle supported on a certain P1. And stability condition punctures this P1.
Okay, so
you remove a point from it, which trivializes the line bundle. This is how it works. So a degree is brought in by tensoring with exterior powers of the fundamental representation of GLN, which we can do because the category is category of equivariant coherent sheaves. or matrix factorizations, you can tensor any object with representation of GLN. So this is our theorem that coherent sheaves, our theorem that you get triple link homology by doing this, triply graded link homology by doing this. The differential that you add to the sum of exterior powers of the fundamental has a very simple form. You take the now you need the stability vector. You multiply it by powers of matrices X and Y, and wedge with the vectors of the sum of exterior powers. So it's your Kazoo generated by this vector. And the claim is that the resulting homology is still an invariant of the link. And it categorifies, this requires a little bit of work, it categorifies Reshetic and Derived polynomial for supergroups. So that's the first extra to the story. The second extra to the story is that you can use what one may call categorified Riemann-Roch theorem here. It's categorified because it's applied to two categories. So the center of this two category is the category of coherent sheaves over the Hilbert scheme. The center defined as endomorphisms of identity functor, endofunctor. Here I skip some details. Just let me just make this as a statement. And we have, Alexei and I constructed the Chern functor, which sends endomorphisms of any object to coherent sheaves. Same as Chern character sends endomorphism of a sheaf to differential forms on the variety. And categorical Riemann-Roch says that home between identity braid tensored with something and any braid is isomorphic to homology of the Chern character to homology of the sheaf complex of sheaves associated to the braid tensored with the sum of exterior powers. So in other words, in ordinary Riemann-Roch, the Euler characteristic of the cohomology of the complex can be computed as integral of its Chern character. And this is the similar statement one floor above. Instead of Euler characteristic, you have home, and instead of integrating Chern character, you take homology of the Chern functor. And this relation was in fact observed many years ago by several people in application initially to the torus knot n, n+1, and that's what started our program. Another extra is that you can replace our main object, T star B, cotangent bundle to flags in our main object with a special bundle over partial flag variety. So take partial flag and take matrices Y, which respect this flag in a prescribed way. So at each I, you make a choice whether you want to send a subspace to itself or to the lower one. So whether you want it nilpotent or Borel at every step. This is something that we explored with Richard Rimani in a slightly different setting. And this will lead to, so the partiality of the flag means that in Hopefully polynomial, you may assign different fundamental representations, different columns to the strands of the braid. And the choice between even in the choice between Borel and nilpotent means, well, let me explain here what it means. Just a moment. If you have an algebra, if you have a group GLMN, it has two fundamental representations. You may denote them as white box and black box. This one would have even M and odd N, and the other one would be the other way, odd M and even N. Both are equally natural. And so when you decide whether your matrix Y keeps the subspace or drops it, it's the difference between assigning a white box or a black box to the strand in the braid. So in this sense, when you in this sense, when you use either Steinberg or Grothendieck-Steinberg, it's the difference between GLN0 and GL0N. So there is this extra which comes naturally in the superstring theory. And finally, just an easy comment related to Rena's work. In this two category of the commuting variety, there is another interesting object. Let me call it SL. That's equivariant Slotoway slice. Just a moment, sorry. Equivariant Slotoway slice. Again, it is a symplectic variety with the action of GLN. So now endomorphisms, just for trivial reasons, endomorphisms of, endomorphisms of the object FLN0 act by composition on home from Slotoway to this. So this is the category that Rena uses. And the action of fine braids on her category in the language of the two category comes from this construction. So you send fine braids in here. And this is how it goes through. So again, a miracle is that equivariant Slotoway is again symplectic, although it didn't have to for this construction. Here is the M-theory superstring explanation. I think I mostly explained it at the beginning, but if you want, I can go a little bit slower over what goes on. And so now you will see where points of the Hilbert scheme and instantons live. So from the physics perspective, you have to consider M-theory, which is a supersymmetric 11-dimensional QFT. And you choose your 11-dimensional space-time as Calabi-Yau of real dimension 6, a hyperkähler variety of real dimension 4, and 11 dimension, let's call it time, will be simply R. And our choice for hyperkähler is C2 with the Taub-Knot metric. So if you assume that Calabi-Yau is compact in quotes, they are not, the interesting ones are not compact, but interesting things happen around certain compact subvarieties, submanifolds sitting in there. So it's compact in the sense that interesting things happen close to the origin. Then you can compactify on CY3, assume that this compact core is small, and your 11-dimensional theory will degenerate into 5-dimensional supersymmetric theory on this hyperkähler cross time. So the goal of all the studies of Donaldson-Thomas and curve counting and so on, everything that happens there, the goal is to find the space of states of BPS particles in this theory. So let me just say, what does this mean roughly? A particle is a particle, similar to electrons, photons, and so on. BPS means that they're in special representation with respect to supersymmetry. There is a very nice metaphor. In fact, it's a particular case of this BPS, which was last suggested to me by Sergei Gukov, and I realized that this is a very good example. Suppose that you study differential forms on a compact manifold with a metric. So you have the action of Laplace-Beltrami operator on them. And you want to find all eigenforms and their eigenvalues. Generally, it's a very complicated thing to do if your manifold does not have a lot of symmetry. So it's impossible. But what you can do is at least enumerate the harmonic forms whose eigenvalues are 0. So all the others will have negative eigenvalues, but the ones who have 0, they're special. So first of all the others will come in pairs related by the de Rham differential and its conjugate delta. So they will form 2-dimensional representations. But the harmonic ones will be in 1-dimensional representations, and they will be killed by both, by D and delta. And moreover, you can count them by using de Rham cohomology, for example. So the states of BPS particles are close analogs of these harmonic forms, and you can count them by considering a topological theory. And this is what happens here, in a sense. So these BPS particles are just accessible. You can count them as opposed to the other ones. Now, the space C2, which is hyperkähler, has 2 C-star actions. One is we call Q and the other we call T. And so if you count those, counting of those BPS particles is equivalent to finding, as far as I understand, the Donaldson-Thomas invariant of this Calabi-Yau. So category phi Donaldson-Thomas would be the space of states of these particles. And the invariant as function of Q would be the Euler characteristic, graded Euler characteristic of that space. So now you do something else. Namely, you bring in M5 branes. Sorry, just a moment. You bring in, just a moment. You bring in M5 branes. So M5 brane I'll say it is an ether. What do you spell ether? That's the medium whose vibrations generate elementary particles. So you place M5 branes, M5. So first of all, M5 brane is 6-dimensional. It's a 6-dimensional submanifold in M11. So if you ignore time, it will be 5-dimensional. It consists of something 3-dimensional, which sits inside Calabi-Yau, and it should be Lagrangian. Maybe I should call it, say Y. And it is Lagrangian. And it's either C sub X or C sub Y inside sorry, my laptop, I'm afraid it's overheated a little bit, misbehaves, inside C2, which is Cx cross Cy, which is our hyperkähler 2.
Do you multiply it silently by line? Because Cx or Cy, they are 2-dimensional.
Yes, so you get, just a moment, you get 5. So this is real dimension 3. This is this or that is real dimension 2. And you also have RT, everything spans RT, and this gives you 6. Why only Cx or Cy? Because you want to preserve the C star actions. If you could put it in some other position inside C2, but then it will break C stars. Now Witten and Vafa, I think, in part say, let us consider a special case where Calabi-Yau is T star is 3. So we still have our Cx cross Cy for HK. And our R time.
So there might be some problem with thinking about T star 3 as a Calabi-Yau.
Well, it is something like x squared plus y squared plus z squared plus w squared is equal to 1.
Yeah, but that's my question, rather whether on which side of the conifold transition you are.
On the side of T star C, on the side of T star C, it is T star S3. So now let us bring in M5s, which wrap S3 cross CX cross, or span rather, wrap is a physics lingo, and N, which wrap S3 cross CX. Oh, sorry, cross CY, of course. Cross RT. From the point of view of 5-dimensional theory, you have a 4-dimensional space, that's our C2, in which now you have these defects. So you have X and you have Y, the coordinates on C's, and you have M defects here, and you have N defects there. And they intersect here. So these defects will vibrate because they're ethers, and they will generate their own photons, so to say. And among those elementary particles, which correspond to vibrations of these ethers and their intersection, there will be special ones, which are BPS, and we want to count them. So Greg Moore will call them frame BPS states. So we want to study frame BPS states corresponding to these defects in this 5D theory, which results from forgetting Calabi-Yau. So counting these frame states together with Q degree, remember that Q scales X with weight 2 and scales Y with weight -2. So counting BPS states is equal to GLMN Chern-Simons Witten theory on S3. So I think this was first observed by Witten. Maybe not exactly in this language, but this is how it works. So if instead of counting them, you look for the space of states of these particles, then you will categorify the Chern-Simons Witten invariant of S3. So this is how you,
if n is equal to 0, it's a Witten, old Witten of 92.
yes, exactly. So the miracle of Chern-Simons theory is related to algebra. Okay, I'm not there yet. Now let's add more. Let's add more M5 branes. So suppose you have a link. Sorry. Suppose now you have a link sitting in S3. And to that link, you associate conormal bundle sitting inside T3S. And this will also be Lagrangian inside T3. Sorry. And this one will also be Lagrangian. So now we add them to the mix. So we add some link-related Lagrangians, let's call them, I don't know, M provisionally, which span conormal cross CX. Well, let me start with CY. Cross RT. Sorry. And let us add in, sorry. Actually, maybe I should have used C, sorry. Maybe I should have used CX. Okay, let's first do CX and then we'll do CY. Some other link. So now there are more ethers, they all vibrate together. So we'll be counting their vibrations, in particular, the ones due to the link-related ethers, and counting those will be related to the Homfly PT polynomial of the total link, except that, again, here I'm simplifying a little bit. So there will be all representations, all fundamental representations showing up. But let me say that, to be specific, let's suppose that n is equal to 0. So I'm talking about SUM theory related to ethers along X. So if I put the link ones along X, that will, so the ones that go along X will be related, honestly speaking, to empty ones. And the ones going this way will be related to these ones. So Kavanov homology is in fact related. Maybe I should have, there is a problem. if you read, first of all, if you read Kaufman's bracket story, you will find that Kaufman assigns minus Q inverse to the unknot. Whereas in Chern-Simon's theory, you assign Q plus Q inverse. There is a slight mismatch. Kavanagh, in his original paper, had to do a lot of extra work with framing, which looked unnatural, because he wanted Q plus Q inverse. He didn't want a minus. So he had to do a lot of work to get plus instead of minus. So these ones will give you plus. Maybe I should go into these details. So,
yeah, I like M theory very much, especially since it's M seminar. But you see, it's too much physics for me, and I do not see still the count on the resolved conifold, which you mentioned in the very beginning.
okay,
It's a nice thing, but it's not quite mathematical.
Okay, so let me say briefly and answer. So first of all, you can push the link Lagrangian submanifolds off the zero section of S3. Sorry. First of all, how do you count the BPS particles? That's question number one. There are lots of ways which will give you the same answer. So one way is to recognize that these are real, genuine particles, meaning ethers in their own right, the material things, not the quanta of vibrations of ether. These material things are represented by M2 branes, which are three-dimensional. So they're one-dimensional in five-dimensional space-time. There are particles moving along their world lines in five-dimensional space. So they're just lines, world lines. And they're two-dimensional inside Calabi-Yau. In this story, they will appear as very thin, infinitely thin annuli, one boundary of which sits on the S3 Lagrangian submanifolds, and the other boundary sits on the Lagrangian submanifolds, which are conormal bundles. So they go along link components. So suppose you have a link component, so there is a very, very thin annulus.
Yeah. I see the geometry. Now you do the conifold transition. Yeah?
Yes, I wanted to mention where Rina sits in this story. So but anyway, before you do the conifold transition, you have to push Lagrangians off the zero section. So first of all, let's present your link. Let's present your link as a closure of a very tight braid.
Yeah, but you wanted to see this way. So I'm not religious about the action of the braid group, but as for the conifold transition, it's explained in this Diaconescu, Schende, and Waffa, which you mentioned.
So we have a braid which goes along some base unknot. It's a very thin braid. And so all the conormal bundles, they sit very close to each other. So now we push them off the zero section of T star S3. So the annuli now become of finite size, of finite radius, of finite width. And on one side, these annuli attach to this tight stack of conormal bundles, and on the inner boundary, they are attached to the stack of zero sections, to S3s. So these are the annuli that appear in, now, since they're tight, so BPS particles are represented by these annuli. More precisely, each particle is represented by their joint vibrations. So studying the joint vibrations of these annuli amounts to the calculation that Rina does. But now we do the conifold transition. And what you see is that these annuli become disks. The inner part collapses, and the inner part sits so this is P1 from the Kani fold. And here we take the fiber of C times C, the fiber of O minus 1 cross O minus 1. And so as in that previous picture, the disks that sit in one of these two C1s, in one of these two Cs, so they sit here. But if you look at the boundaries, they're not quite aligned with each other because they end on different strands of the braid. And the braid points will show up in the others.
So sorry, I'm confused. I saw just one disk. Where is the second one?
They overlap in that C. If you ignore the other one, they overlap. If you see both, so here I use just one R from this C. So this is some R inside this C. So now I can draw the other C. So here I'll see the sections of those disks, but there are different positions in this C. And if you project them, these are the points of the braid. And if you project them down, you see the section of the disk picture. So you see something and you see something else, and they overlap. And so here you have multiplicity 2, and here you have multiplicity 1.
So then your BPS count, it becomes...
Not yet. Not yet. We have to do something else. The problem is that BPS counting in M theory is very complicated. So physicists tell us that we have to go to strings. In order to go to strings, we have to select a U1 subgroup, which acts on M11. And hopefully having orbits of limited radius. And we take the quotient of M11 by this U1, which will give us M10, maybe with singularities. And so so we assume that all the radii are small. So we get an effective theory, which is now 10-dimensional space-time. And that will be a superstring theory of type 2A. Now with conifold, we have a choice. The usual choice that will lead you to, most people do the following, that will lead you in particular to Diaconescu-Shendewafa. They will use U1, which rotates the Taubnut, the hyperkähler. They will use the one that rotates the C2 there, which is the U1 which gives you Q degree, whose weights are related to Q degree. So the Calabi-Yau will remain intact, but you will lose your hyperkähler. So you will not see the, so if you see Hilbert scheme, it will come from somewhere else. I should have said that the points of our Hilbert scheme and our instantons are moving on the hyperkähler. So the instantons, okay, I'll say it a little bit later. So everybody compactifies hyperkähler, but then the Q degree becomes rather complicated, non-transparent, because you compactify it by its action. It becomes something strange. So what we use is a symmetry of the conifold, which rotates P1 and rotates both O-1s in such a way that at the North Pole, you do not rotate the O-1, which supports the disks. It remains, so you rotate the base in the other O-1 at the North Pole. And at the South Pole, they reverse. So at the South Pole, the fiber of the other O-1 is rotated.
So it's weight 1 minus 1.
Yes, so that's the
The
action.
square and your infinity is stable. Oh, it's not. Oh, no, you say that it's rotates CP1 too, but what about the point where your C square lives? Is it also rotated or?
So it rotates. Oh, I forgot how to say it clearly, but I will tell you just with certainty that at the North Pole, the base will be rotated and the second C will be rotated. At the South Pole, the base will rotate and the first C will rotate. So
Yeah,
anyway,
the action on the fixed points of the whatever C star action on CP1.
so
Yeah.
the fixed points of P1 are North Pole and South Pole.
Okay, and they're stable, but there is some action on the fibers with weights which say 1 minus 1 or something like that.
Sorry, 1 and 0. So it's, let's say it's -1 on the base, 1 on this one, and 0 on this one.
Okay.
I do not want to rotate the disks.
Mhm. Okay.
But the braid points, the plane which supports braid points is rotated. This is the second C. It is rotated. So you lose the angular coordinate of braid points. So the braiding becomes mysterious. So the Q degree becomes apparent, but the braiding becomes mysterious. You don't see the braiding naturally. It becomes a strange sheaf. So you lost the angular coordinate of braid points, and but you keep the Q degree as action on some variable. Since the plane supporting disks is not rotated, M2s become D2s. They become branes D2 of the superstring theory. And the physics of their stack is well known. It's described by supersymmetric quantum field theory, sigma model.
Yeah, but geometrically, are they, I do not see them. They should be some complex curves.
That's the beauty. You do not need the curves anymore. And you do something else, which is called B-twisting. After you do this, you do not care about the shape of the curves. It disappears. All you have is a 3D B model, which maps your stack of disks into the Hilbert space of points, living in the untouched C2, in that extra, in the hyperkähler.
Okay. Okay, and this
Because
configuration of points is kind of described sort of, so it would be naturally to place your curve in this C square in the fiber, but you say that I should consider only infinitesimal neighborhood.
Yes.
Of the intersection point.
So
okay. All right, and so then I have configuration of points on C square, which is a point in the Hilbert scheme. Yeah.
In fact, string people tell us that vibration of a stack of D branes in transverse direction naively would be described. So if you have n D branes which form a stack, and you want to describe their vibration in transverse direction, naively you would need n scalar functions, each describing the coordinate of a particular. But physicists tell you that in fact it's an n by n matrix whose eigenvalues. Well, okay, so
no, I mean, I'm thinking about this. I mean, algebra geometrically, it's quite obvious. You have something like fat divisor.
Yes.
So then you can think of this coordinate z in the power n equals 0 as an n by n matrix, whatever. Yeah, I mean, Yeah.
Jan, it's a bit different. Sorry, it's not the it's a different logic, but nevertheless it's a matrix. So that's how you get X and Y matrices of the Hilbert scheme. The framing comes from the fact that this U1 action preserves the second fiber at the North Pole of P1. That second fiber is stable. As a result, it produces what's called a D6 brane. So the framing vector is a string which is attached by one side to that D6 brane, and the other end is attached to the stack of D2 branes. So strings tell you that there is also framing.
So then conventionally, I would say that I should count something like D6, D2, and
yes, it's
maybe
about
D0 bound states.
There is no D0.
That's
okay. Another beauty. D0 will happen if you compactify the hyperkähler, the C2 which exists separately, the HK. If
okay,
you use
all right.
the one,
so then, okay, then I have to, okay, my D6 is my resolved conifold, probably, yeah. And so I still kind of, you see, I get used to more.
but by the way, you lost, I'm sorry, Jan, you lost the conifold because you took quotient by the action of U1. So conifold becomes R5, tells me
where is my D6 then?
D6 sits inside that R5. In fact, in that R5, you will see two D6s. One D6 is, so you'll have one D6 and you'll have another D6. This D6 supports the stack of D2s. This is one D6. So you have a string which here everywhere begins here and ends there. And this is your framing vector V. And you also have their perpendicular one string which connects this D6 in the center of this stack of D2s. And this one generates the sum of exterior powers of Vn in the story about A degree. This is originally, you know that A degree comes from M2s which wrap P1, the base of
really don't like R5, which you have, but you say so.
Okay, Tudor told me that if you take this resolved conifold and take the quotient by this U1, then you will get R5, he told me.
Yeah, at least 6 minus 1 is 5. So.
Yes, yes, of course. This I could figure by myself.
Yeah, but there was kind of a much older story about this Homfli PT, in which Alexei also participated, the Oblomkov, Shende.
Let me tell you
how to see it here.
Yes. So they did something different. Namely, they compactified HK. So they had their conifold unmolested. Instead of HK, they got R3. They got a D6, a single D6, because Calabi-Yau was not moved by U1. U1 moves only HK, so you get D6, which
spans. So my conifold survives then.
Yes, so your conifold survives. It's spanned by one big D6. Inside that D6 lives your curve. Now you have to study the curve. You get the, for torus knot, you know what it is explicitly.
Yeah, all right. Yeah, and this is traditional story.
Yes.
All right. Yeah, and
you can still apply the same logic for any braid and smash it. And this is what we're studying with Tudor and other people.
Yeah, so, you see this BPS count, or rather DT or PT count, in that old picture, it's quite understandable because it's algebra geometric. count. You have a curve in UC square with a singularity at the intersection with, say, North Pole, if you placed, and then you consider sort of coherent sheaves which can have support either on your CP1 or on that curve.
Yes.
So this is sort of mathematically clear.
Here it's even better. You have a stack of disks. So let me just a moment.
So I'm wondering about the mathematically well-defined enumerative problem.
Oh, there is no enumeration. It's a B theory, so it's a B side. So you don't have to look for solutions. You don't have to enumerate. You have to compose matrix factorizations. So you have a 3D theory.
All right. So then okay. All right.
So here is a picture. This is a stack of disks. And so far, I compress their borders. So I do not distinguish the borders of individual disks. I just have one single disk.
Okay.
So this is the space-time is a thick cylinder. Sorry, it's a solid cylinder. And I'm just taking its section. And the space of BPS states is equal, that's the particle wave duality, so to say. The space of BPS states is equal to the space of states of this disk. So I have to find the space of states of this disk.
All right, but mathematically it's...
On the border of this disk, I see elementary braids, which I draw here as lines. So here I see points where my braids live. Now, if I consider a cut here, to this cut, I associate, and so on every segment, I have the same object. On every segment, I have the same object FL, which is, and these objects are separated by these pink, purple points. So to this green arc, one associates endomorphisms of FL, the category of endomorphisms, and to this particular pink one, beta, since this half disk bounds the green one, this means that beta becomes an object in this category.
Should I think, sorry for a stupid question about this brane as a kind of a line operator in some?
Yes, so elementary braids become line operators on the boundary of the solid cylinder.
Okay, and so this why endomorphism is a monoidal category.
Yes.
Yeah, okay, good.
So if I want to know what sits here, I have to compose this and that.
Yeah, so then geometrically everything simplifies, but the definition of FL becomes very complicated.
Now let me explain where FL comes from. Why is it FL? So here we see two quivers, in fact. Vibration of disk is described by B model of Hilbert space. Well, let's make it simple. Let's ignore the framing. So here we have different multiplicities of disks because some disks n. So for example, here I have multiplicity n plus 1. Here I have multiplicity n. Here I have multiplicity n minus 1. Because those disks at the boundary end on the consequent Lagrangian submanifolds. So inside each area, I have a B model with a different target. So here the target is this quiver variety. Here the target is this quiver variety, and here it's n minus 1. And they're separated by these green defects. So to a defect, I have to associate a Lagrangian correspondence. So there is a Lagrangian correspondence between, say, two commuting varieties. how would I describe it? I would describe it again by generating by this action thing. So if here I have n minus 1, sorry, if here I have say n and n plus 1.
But in the case of, hold on, in the case of framing like Hilbert scheme, it's not something like coherent shifts on Nakajima correspondences. Is it categorific? No.
So we're drawing a picture of a space slice of a three-dimensional theory. So to each region here, we associate a symplectic variety, and they're separated by these green defects, which are two-dimensional in the solid cylinder. So in the solid cylinder, the green ones would look like cylinders. But in the section, they look like circles. These defects are associated to defectively associate a Lagrangian correspondence between neighboring symplectic varieties. So in order to describe Lagrangian correspondence, I pick auxiliary variety, which is this arrow and this arrow. So let's call them, I don't know, phi and phi prime. And here I have my base is described by matrix x1 and here by matrix x2. This one is from GLN and this one is from GLN plus 1. And my W, sorry, which will describe the correspondence, will be trace of x2 with I may put them in the wrong order, but you understand. Minus x1 phi prime. So this describes this is a nice description of Lagrangian subvariety, separating two commuting varieties. So if I want to describe the whole boundary, I have to compose these Lagrangian subvarieties, do the convolution. And how do you do convolution? You declare each intermediate X matrix, you declare it to be another auxiliary variable. So if you want to go, say, from 0 to 1,
you will have kind of a very large auxiliary space.
Yes, but then you can simplify it with the help of Knorr and basically Knorr, and you will see that you end up with the flag variety. So what you see here is that the correspondences form edges of the second Nakajima quiver, which is not surprising. From the string point of view, we see here two stacks of NS5 branes which intersect. The usual Nakajima quiver comes from a stack of NS5 branes and some let's ignore D5s. But here we have two stacks of NS5s. There is a single NS5 which is related to T dual of Taubnat. It's hidden, it's related to Taubnat, and there is only one. And there is a stack of NS5s which is related to link components. So both give you quivers. The link components give you a linear quiver. The Taubnat gives you the affine quiver. And now, from the point of view of the physics of D2s, you have these affine ones separated by green lines, but green lines combine into the second quiver. So you may say that you have a Nakajima quiver, linear one, but inside each circle you secretly have commuting variety. And so these are phi arrows. So whereas you see, what does Nakajima do? He does Hamiltonian reduction at every quiver node. We're doing a sort of derived Hamiltonian reduction. A derived Hamiltonian reduction means that you set mu1 minus mu2 equal to 0 either through Kazoo complex or by introducing an extra matrix X, which multiplies mu2 minus mu1, and taking trace and declaring it as a matrix, as a W for matrix factorization. So that's so this is so we bring a second symplectic story into the standard Nakajima story.
Yeah, it's a bit.
There are two unrelated symplectic stories, which suggest certain generalizations. In our work with Richard Rimani, we suggested varieties. So Nakajima has varieties for representations of GLN. So there is a question: what should you use for representations of superalgebras? And there is a simple answer, and it comes from playing with Legendre transforms by using the second symplectic structure here. I'm sorry, I'm a little bit off of the subject. So the point is that individual lines are Lagrangian correspondences, but they compose into the second Nakajima quiver. Now, if you have a framed version, now let's see if I remember this. For example, if you want to describe Lagrangian correspondence between Grassmannian quivers, you may use this one, and this one. Do I remember it correctly? We have it written up in one of our papers with Alexei. So now here you're using this one, yes, and this one as your, so your Grassmannian is cotangent bundle to vertical blue arrow. So if you introduce pink arrows, then each triangle gives you a piece in W. You just compose them and take the trace. And this, so pink ones are auxiliary variables, and this describes a nice Lagrangian correspondence between two cotangent bundles to Grassmannians, which says, of course, that one subspace should be the subspace of the other, and then you take a normal bundle.
May I ask a slightly perpendicular? It's already discussion, you know.
Yes. Any question is very welcome, because very few people would listen to this.
Okay, so far at least 10 people are listening, but maybe if you continue, very few will listen. No, the question is like this. Since you mentioned Tudor and maybe in Gukov,
yes.
Anyway, some friends. So they had some work about vertex operator algebras associated to some, well, whatever, three manifolds, or more generally, they come from this 3D gauge theories. Now, if you include the link in the story, will it give you some representations of that vertex algebra? First, from the perspective of this BPS count, you know, it's all the idea that there is a BPS algebra, which, and if you have some defects, some, I don't know, like links, then there are modules for this BPS algebra. So then if
Jan, this part I honestly do not know. I can tell you. So they use the fact that 6 equals 3 plus 3. So I can tell you what their 3 and 3 are in the picture, in this 11-dimensional picture, but I do not know about vertex operator algebras yet. So I hope to learn it eventually.
All right, 1, 3 is what? Calabi-Yau?
So let me say that 1, 3 is S3, the base of T star is 3.
Okay.
So that's one theory. And the other one is, say CX, yes, CX cross RT. So it's something spanned by these M5 branes. It's 6-dimensional. Now this CX has a shape of cigar because of the Taub-Knot metric.
And your braids, they are kind of.
So this is they interpret this as a boundary.
Yeah.
So their vertex operator algebras somehow sit on the boundaries. So the whole 6-dimensional theory somehow splits into a topological theory on here and a supersymmetric theory here. So supersymmetric one gives you vertex operator algebras. Jan, honestly, I have to learn a lot about that.
Yeah, me too. All right, maybe since kind of occupied all the time, are there any other questions? To the speaker. Because at least I don't know, maybe Irina or whoever is left.
I actually have a question, but it's so it's very possible that you have already answered it and I just missed it. So you said that there are several examples where varieties are, so in some examples certain varieties are symplectic, where in fact it's an unrelated thing for them to be symplectic. Do you have any examples where with non-symplectic varieties in
yes, this is what happens when you try to change the color of boxes. So for example, instead of just a moment. So as our basic object, we could use n tilde, which is T star B, which goes to GLN. In fact, to nilpotent, or we could use G tilde, which also goes to G. So this one is symplectic, but this one is not symplectic.
Oh, I see.
But still plays a role.
Yeah. Yeah, so there is still a fine break group actually.
Yes. So this is related to the fact that GLN, sorry. Well, I can say, I could say that GLN has two representations, the even one and the odd one. You would ask me then, why consider odd one? Why even bother? And the answer would be that if you think of GLN as GLN0, then the even one would be natural and the odd one would be, then versus GL0n.
Yeah.
Then whoever was even will become odd and vice versa. So in terms of Rashtikin to Rive invariance, the distinction is minor, it's just a sign. In terms of categorified invariance, the distinction is major. It's well, it's different homology. The wrong one is much bigger. So again, for me, the trouble started when Misha tried to turn minus Q inverse into Q plus Q inverse. when we wrote our paper on matrix factorizations, there you can clearly see that minus Q inverse is the natural choice. Yet he wanted to keep it positive. So the distinction is that the easy Rashitikin derive comes from even VN, but Misha's homology comes from odd one.
Right.
Again, let me explain. It has a very simple physical explanation. In that extra C2, if your Chern-Simons producing branes go like this, and your link producing branes go like this in this extra dimension, then the particles which are related to both are stretched between them and are concentrated here.
Mm.
So therefore, there are only few states. That's how Misha gets finite dimensional homology.
Right.
However, if you send both along X, then they can run along X. And you will get infinite dimensional space, at least due to the fact that they can travel. So, but they will have the same Euler characteristic. But one will be finite dimensional and the other one will be infinite dimensional. In fact, it will look like, in the simplest example, if you use the wrong box, the other box, then your SL2 homology will look like triply graded homology, exactly the same. The differential will be zero somehow in that case. It's not always the case, but the particle then can run. Sorry, 11 dimension helps. It gives you, at least it gives you some suggestion about what you should get and what you should.
Thank you.
In your case, one can also do the superalgebra version. And that's part of what we were doing with Richard Remanier. But that's a little bit separate story, but your category can be adapted, except that I don't know how to get the link invariance for links in S3. It's a little bit separate story. So as an advertisement, we have varieties, Nakajima type, let's say, which can be used to categorify representations of superalgebras and wrong representations of ordinary algebras. You see, if you use the wrong box,
Yeah.
and instead of exterior powers, you get symmetric powers.
Yes.
So with the other variety, you will naturally get representations coming from symmetric powers instead of.
Right.
And
Yeah. So you want superalgebras to decode the exterior picture.
Yes, so if you use the wrong box, for you the distinction will be that instead of cotangent bundle to flag, you will use the Grothendieck type. If you try to intersect it with Slodowy, you will see that it works. You get non-trivial intersections where you would get trivial intersections for nilpotent fibers. And this corresponds to the fact that you get symmetric powers instead of skew symmetric, so you can go infinitely far.
Yeah, thank you. It's very interesting. I'd love to talk more to you about that. I can email you later.
All right. So more questions? Well, if not, Lev, I ask you to email me kind of your notes, including the discussion, because it's my understanding that the discussion has been recorded too. And so then there will be some illustration to the discussion too.
Yes,
right.
I'll send it shortly.
Yeah, very interesting. It's kind of.
Thank you very much for listening.
Yeah, and thank you for giving this talk. Yeah, it's more questions than answers. But anyway, thank you very much. Yeah, so I see some people send uploads to you. Like, okay, thank you, Lev. And probably this is it. So we close. I think this is the longest seminar.
Oh my God. Okay,
No, but it's very good.